Hello everyone, my name is Gregor Weiss. I'm a professor of finance here at Leipzig University, and in this video I want to show you how penalized linear regression models work as part of our class in artificial intelligence and machine learning in finance. So we've already seen multiple linear regression in action and its details, and we now want to move forward to penalized regression. As the name suggests, you can imagine that it's some kind is a sort of regression analysis that penalizes in its objective function certain aspects of our modeling. And if you recall the problem of model selection or variable selection, we saw that one can do subset variable selection, either forward or backward stepwise selection. That is, you start, for example, with a null model and then you slowly include more and more variables, or you start with the model that includes all p predictors and you exclude those predictors that don't add too much to the model's fit. Now, the alternative approach here, which is much more feasible than actually subset variable selection, are shrinkage methods, or alternatively, as we call them, penalized regression. So what is penalized regression? Actually, in penalized regression models, we use all p predictors, that is, we use all variables that might explain our response variable, and we use them all in one model. And in contrast to subset variable selection, the coefficient estimates are constrained, or we also call it regularized, which means, in other words, the different algorithms shrink the coefficient estimates towards zero, so that some of the variables actually have a coefficient that is close to zero or equal to zero, but all variables are included from the start. And actually, we'll see in the case of rich regression, all variables, all predictors actually stay in the model, because most of the coefficient will be close to zero, but they will not be equal to zero. So these are penalized regression models. And we'll start with so-called rich regression. So remember, in ordinary least squares, we try to minimize the residual sum of squares, the RSS, which actually here is given as the sum of the difference between yi, the response variable, and the intercept, of course, and the sum of the coefficients times the predictors. So actually, if you look at this equation, we can see the response here, and actually this is nothing but our estimate and our prediction. So this is, for example, f hat of xi. We could have also called it hat yi, and then we take the difference, we square it, and we sum it all up, and we get ordinary least squares. So that's the case of our previous section. Now, in this variant of OLS, rich regression, we still minimize the RSS, but we include this additional component, which is tuning parameter lambda times the sum of the squared coefficients beta j. Be careful that we do not include the intercept here, but we only include the slopes for all those p predictors. So we start at j equal to 1, and we do not touch beta 0. In other words, it's simply the RSS. We also try to minimize in OLS, but we have this component, lambda, the tuning parameter, times the sum of the squared coefficients. Now, what does this mean? It means that actually, because we are trying to minimize this, the squared coefficients are non-negative, and actually the tuning parameter is also non-negative. It's larger or equal to 0. So this means that actually, as we're trying to minimize this, we are penalizing coefficients that are not equal to 0. So ideally, we would see that at some point the coefficients will tend to go to 0, and this is governed by the tuning parameter lambda. Now, as you can see, if lambda is chosen to be equal, then we get OLS. So OLS, ordinary least squares, is actually embedded in rich regression as the special case for lambda being equal to 0. Okay, so that's rich regression. As with OLS, rich regression seeks to find a model that first of all fits the data well. So we're trying still to minimize RSS, but we have this shrinkage penalty, lambda times the sum of these squared coefficients, and this is small when the parameters beta j, not the intercept, the slopes, are close to 0. So the parameter lambda controls this process of shrinking the parameters towards 0. And as I told you, actually if lambda is equal to 0, we get the ordinary least squares estimates. And if lambda tends to go to infinity, actually the rich regression coefficients will all be 0, because then the effect of this shrinkage penalty will be infinitely high and the coefficients will be shrunk to almost close to 0. So this is what happens to the rich regression coefficients. But as you can see, with every different lambda, we get a different set of coefficients. So one has to be careful when comparing OLS with rich regression, because OLS only fits the model to one set of coefficients, to the data, and we get one set of coefficient. In rich regression, actually, we will do this and repeat this for several values of lambda. So actually, we'll compute 10, 50, maybe even 100 models, and we get different coefficients for different values of the tuning parameter lambda. To see how this works, we can have a look at this plot of different coefficients for different lambdas. On the left hand side you can see here we have lambda on the x-axis and the standardized coefficients for variables like income, limit, rating and student. You remember these were predictors used to predict the balance on your credit card, and we're using the credit data from the James Whitten, Hastie and Tibshirani textbook. As you can see, if we start out here with lambda being close to 0, actually those should be the OLS coefficients for those predictors. But as you can see, if we now increase lambda, you can see that actually we have a couple of other predictors here, but they are already very close to 0. You can see that with increases in lambda, some of the predictors are forced to a value of 0 quite early, like for example income, it starts to decrease very early, in contrast to, for example, actually limit even starts before that, and for example student remains constant for some time and then goes down at some point. On the right hand side here you can see that at some point lambda is so high that all those coefficients, all those regression slopes are close to 0. So this happens here. On the right hand side you can see this in just a different way of telling the story. You can see the rich regression coefficients beta for different lambdas divided by the OLS coefficients, and you can see that now these are the OLS coefficients. This is when they are actually the same, and here for most of these predictors they stay close to 0, but some like income, limit, rating and student, they are significant in OLS but also in the rich regression. The question, first of all, what should we do and what should we be careful about? With OLS, you might know that the coefficient estimates are scale equivariant, which means that if you rescale a variable, then the OLS coefficient will be scaled by that factor. This is not true with rich regression. Actually, the coefficients can change when the predictors are multiplied by a constant. And thus we should always use standardized predictors. That is, we take our predictor values xij and we standardize it by the square root of its sample variance. And in this case, the standardized predictors in our sample have a standard deviation of 1. Each has a standard deviation of 1. And as you can see here, this is done for the jth variables. So the jth predictor, we take the standard deviation of the jth predictor, and if we divide each observation by the standard deviation, then it has a standard deviation of 1. So that's what you should always do. Now, one could ask, and this is the obvious question: why should we care and why should we consider using ridge regression over OLS? And what are the advantages of ridge regression over ordinary least squares? Well, the answer lies in the bias variance trade-off. If you recall the training mean squared error, we've already seen the mean squared error, which was simply defined as 1 over n times the sum of the errors in our data, and those errors were squared. We would get the mean squared error. Now, if we do this in the training data set, then we would get the training mean squared errors. Later on, we'll see that we should actually do this based on a model that has been fitted to the training data. We should check the mean squared error for a previously unseen test observation, let's call it x0 and y0. Then we would get the test MSE, just to make sure that we're not checking the validity of our model based on the data we've used for fitting the model. Now recall the training or the test mean squared error. Obviously, this is a proxy, this is a metric of how well our model fits the data. Now, you can show that actually if we are interested in the expected test mean squared error, so the expected error on average, if we square it, the error of a test observation which has not been used in fitting the model, which is on the left hand side here. Let me highlight this for you. This is the expected test mean squared error. This is actually decomposed into the variance of f hat at x0 plus the bias squared of f hat at x0 plus the variance of the error term. We cannot do too much about the variance of the error term, but actually we can see that we have the variance of our fitted model at the test data plus the bias. Now, to minimize the test mean squared error on the left hand side, we can see that actually we have two levers. The first one is variance. It refers to the amount by which our fitted function, our estimated function f hat, would change if we estimated it using a different training data set. Now, assume we have this data set and we have this test data observation. Now, if we estimate our model, if we fit our model to this data set and we check the expected test mean squared error using this test observation, then obviously we get one mean squared error. But what would happen now if we had a different training data set and we had the same or a different test observation? Would we still get the same error? Now, the variance here refers to the fact that if we use different data samples for fitting our model, for training our model, we probably will get a different estimate for the response at x0, so we get a different mean squared error. The bias, on the other hand, refers to the error that is introduced by using a model to approximate for the unknown function f, that is, that we use a linear model. Now, again, we want to estimate a function f. We don't know per se ex ante if f is linear, if it's polynomial, can be any nonlinear function as well. So actually, if we have this training data sample, what error is introduced by the fact that we're using the assumption, for example in OLS, but also in ridge regression, that we're using a linear model to estimate f. So that's the bias. Okay, so you can see that actually the expected test mean error here, this is actually due to the fact that, first of all, we might have the wrong model, that is the bias, and it could be due to the fact that, yes, we have the right model, f is approximated correctly by, for example, a linear model, but if we use different training data, we still get a slightly different approximation. And you can see this quite easily if, for example, we assume that we have a training data set that only includes n equal to 5 observations, and again 5 different observations. Now it's clear that we might have the correct model, but because of the fact that we are using a finite sample, we only have 5 observations in our training data sample, there is a lot of variance in our model estimation, and that's the variance. So we have two things we need to care about, variance and bias. And actually, it's easy to show that if you increase, or actually if you decrease variance, you increase bias, and vice versa. So you cannot reduce both at the same time, but usually it's a trade-off. If you have lower variance, you will probably have higher bias. Yeah? So this is shown here with simulated data. Let me get my red line here again. So this is simulated data, and the data is simulated in these are the simulated observations, those black circles. The true model is actually given by the black curve. So it's a polynomial function, and that's the true model. But because we are simulating from this model, we still have some randomness in our observations given by the black circles. Now we can use a linear model. That's the one in orange here. And we can use smoothing splines, which is very similar to, let's say, polynomial. You might know what a spline is. I don't want to go into detail here, but these are smoothing splines, polynomial splines, in blue and green. And you can see the blue line is doing okay. It's actually pretty close to the black curve, so that's probably our best model. And as you can see, the green curve is close to the black circles, but it's actually quite far away, as you can see here, from the black curve. It's close to the points here and here, but it's rather far away, and it's modeling, it's fitting the noise in the data. It's fitting the noise introduced by simulating from the black curve. So what can we see on the right-hand side? Actually, we can see the flexibility on the x-axis and the mean squared error. And actually, the red curve is the test MSE, and the gray curve is the training MSE for those different models. Here you can see the OLS model, the linear model. As you can see, the training MSE and the test MSE are quite close here, and actually quite high. If we use the smoothing spline with the blue curve, you can see that actually they are still quite close together, and actually lower. And we can actually reduce the training MSE by using a much more flexible model. For example, we can also make it very extreme and use a curve that goes through all these black points. But you can see it's rather wiggly, and actually you get my idea that actually you are just fitting noise. And what will happen is that actually the training MSE goes down because we're using a more flexible model. But as we are fitting the model to noise, if we now use a different data set, that is the test MSE, it will increase. And we are using a different data set, and suddenly the mean squared error, the test mean squared error, goes up. And this shows you that what happens. By moving from the blue curve to the green curve, we are decreasing the bias. There's no bias in this red curve. It's fitting the data points perfectly well, so we don't have any bias, but it significantly increases variance, because if we are now using the model on a different data set, we suddenly get a model that no longer fits the data quite well. So that's the bias variance trade-off. And coming back to ridge regression, if we now increase lambda, we are decreasing the flexibility of the ridge regression, and the bias increases. And this is shown here. For example, we can see with the squared bias in black, the variance in green, and the test MSE, which is, as we've seen before, actually can be decomposed. It can be seen as a decomposition of the test MSE. This now shows that actually the test MSE in purple can be reduced by moving from OLS to this point, which gives us sort of an optimal tuning parameter lambda, because now we can decrease the test MSE from, let's say, it's maybe 48 to maybe 35. So this is what happens. Ridge regression allows us to exploit the bias variance trade-off and to reduce the test MSE by tuning or choosing a tuning parameter to minimize the test mean squared error. And this is quite clear here from the ridge regression. Another advantage is if P is larger than N, if we have more predictors than observations, then the OLS estimates do not even have a unique solution, so we might be inclined to use ridge regression in the first place. It also has computational advantages over OLS combined with best subset selection. That is, in ridge regression, we're using all predictors. In OLS, this would be done by best subset selection. That is, we would need to estimate 2 taken to the power of P models, and this quickly becomes unfeasible. And ridge regression has one serious disadvantage. It will include all P predictors in the final model, and almost always it will happen that the coefficients will not be equal to 0. And this is why one can then move on to the so-called Lasso. Lasso is the least absolute shrinkage and selection operator, and ridge regression, as we've seen, will always generate a model that includes relevant and irrelevant predictors, because most of the predictors will not be equal to 0. However, we can remedy this by using the Lasso. The Lasso coefficients minimize the following quantity. Again, we minimize the RSS, and we are using a slightly different penalty term here. We are not using the squared coefficients, but we are using the absolute coefficients, with lambda again being a tuning parameter. Now this seems to be almost equal to the ridge regression. The difference, however, is that, in short, Lasso uses the so-called L1 norm, the absolute value of the coefficients, whereas ridge regression uses the L2 norm to penalize too high coefficients. Now the advantage of Lasso is that by using the L1 norm, this forces some coefficients to be exactly equal to 0. So these predictors will not pop up in our final selection, in our final model fit. Hence, Lasso performs a variable selection, and fitted models are sparse. They do not include all predictors, and this makes interpretation of the final result much easier in contrast to ridge regression. And this is what it looks for the credit data. We've seen with ridge regression, those parameters will slowly approach 0. But here you can see, for example, with income, it already becomes 0 here, and all those other predictors, they have 0 coefficients that are equal to 0 at this point, and this is the difference to ridge regression. To explain why this happens, we can simply look at this plot, which gives you the contour plots of OLS, of the RSS. This point here, the black dot, that's the OLS coefficients. That's the minimal point if we don't have any constraints, if we don't regularize this. And what now happens is that with the ridge regression and Lasso, this is actually the Lasso, this is the ridge regression. We are using the L2 and the L1 norm, and we only allow coefficients, for example, that are in this turquoise rectangle or in this sphere. Now, to show you what happens with ridge regression, for example, if we only allow these coefficients, then we are looking for a minimal RSS on the border of the sphere. If we now increase the sphere, you can see what it happens is now we are looking for a minimal RSS. Disregard the last one. And what happens is, for example, it's too small, too large, I guess. For example, this will happen, and you can see that now we have a point where actually the sphere touches a contour plot. And this then is the optimal point, the minimal point with the penalty term. So this would be beta 1, and this here would be beta 2. Same if we increase our tuning parameter, then obviously if we have a larger sphere, then for example, to be centered around 0, then we would use probably, let me just see, it touches probably a contour plot that looks like this, then we would get non-zero coefficients, beta 2 and beta 1. Now, you can now see why Lasso forces one coefficient to be 0. It's the same, but because we're using a rectangle, this here will always touch a contour plot of the RSS at some point where beta 1 or beta 2 is 0. So in this case, beta 1 is 0 and beta 2 is not equal to 0. And this is why, geometrically speaking, why Lasso forces some of the coefficients to be 0. Okay, so which performs best, ridge or Lasso? Well, neither ridge regression nor the Lasso will universally dominate the other. As a rule of thumb, you should use Lasso if you have a relatively small number of predictors that are expected to have non-zero coefficients. For example, if you have 1,000 predictors and you only expect 5, 10, maybe 20 of them to have non-zero coefficients, you should use Lasso because you're not interested in hundreds of coefficients to be close to 0 but not equal to 0. In ridge regression, you should use ridge regression if the response is a function of many predictors, of let's say all 100 or 1,000 coefficients predictors, and all coefficients are roughly of equal size. Then you should use ridge regression. Okay, so next we'll have a look at the application of these models in practice.